Hi guys, today our lesson is on bond polarity and dipole moments. In our chapter 8, we discussed polar bonds and bond dipoles, but one thing you need to understand is just because a molecule possesses a polar bond or a polar covalent bond, that does not necessarily mean that the molecule as a whole will be a polar molecule. By adding the individual bond dipoles, one can determine the overall dipole moment for the molecule. So it has to do with the symmetry within your molecule, the way the electrons are arranged around your central atom. Here you see a ball and stick model of carbon dioxide. And when you draw the vectors, which are these arrows here that represent the direction the electrons are being pulled in, you see that the vectors are equal in magnitude but opposite in direction, so therefore they will cancel out. So a molecule of carbon dioxide, even though it has carbon-oxygen polar covalent bond here and a carbon-oxygen polar covalent bond here, the vectors themselves cancel out due to the symmetry in the molecule. So carbon dioxide is known to have no dipole moment. Now, in water, because water is a bent molecule, because you have the extra lone pair of electrons sitting here and here, when you draw the vectors pointing towards the arrow points towards your most electronegative element, indicating that it's pulling the electrons towards it, oxygen is going to get a +2 for its partial charge because there's two arrows pointing towards him, and hydrogen gets a +1 partial charge here and a partial charge here. But notice that the direction of the vectors are at an angle, so they're not opposite in direction. They are equal in magnitude, but when you have vectors coming at an angle, what you have to do is take the resultant vector, which is an average of the two, which would be this vector you see here, pointing up right in the middle, kind of splitting the two. So there is a net vector left over. So we would say that water, because of its bent structure and its asymmetrical structure, has a overall dipole moment. Now, let's consider a molecule or several molecules here that you see of hydrogen chloride. This is a linear molecule. Chlorine is your most electronegative element. So you would draw your vector pointing towards the chlorine, indicating it is pulling the electrons towards it. They're spending more time around the chlorine. And so if you were to have, say, here I have 3 hydrogen chloride molecules and I throw them into a magnetic field, they would all have a preferential alignment when you place the HCl in this electric field. Now that preferential alignment or preferential orientation in the magnetic field, what that means is it has a center of positive and a center of negative charge. So we would say that the molecule has a dipole moment or it is dipolar. Here's the vector. When you draw your vectors, the positive end is going to be at the end of the atom in the molecule that has the least electronegativity, and the arrow will always point in the direction of your more electronegative element. So I've talked a little bit about vectors. I've mentioned those on the last 2 slides. So let's just get into that a little bit more in detail. We do use vectors to represent a polar bond. Now vectors have magnitude and direction. And the way vectors work is if you have 2 vectors pointing in the same direction, like if I had this vector here, and if I had another vector, let me pull my pen up here. If I had another vector exactly like it, pointing in the same direction, let's assume these are equal magnitude, then you would add them together. Let's say this is 1 unit, and this would represent 1 unit. We would say we had a resultant vector that would be an addition of the 2 of pointing in the same direction that would equal to 2 units. Okay, now these are not to scale, but if you add these 2 together, you would have a resultant vector of 2 units. Now, if you were to have 2 vectors pointing in opposite directions, say this vector here, and then you had another vector pointing exactly opposite, that was 1 unit. Since they're in opposite directions, you would say they cancel out. So it's kind of like a +1 and a -1. Since they're in opposite directions, you would subtract. If your vectors are ever at an angle, like coming at an angle towards one another, you have to take their average, which I always kind of represent with a dashed line, and the average would be kind of right in the middle, pointing in the same direction that the two initial vectors were pointing in. Now, any two-atom molecule that has a polar bond, remember the polar bond is when you have an electronegativity difference between 0.5 and 1.6. Let me try to get rid of these. Okay. Will show a dipole moment. So this is the HCl. It's just a two-atom molecule, and it is a polar covalent bond if you do the delta X. So there's no vector to cancel with that. So you would say it has a dipole moment. There are some polyatomic molecules that also exhibit dipolar behavior. Now, how do we know when we have a dipole moment? Well, it's when the vectors do not cancel out. Like with the water, notice the vectors are coming at angles, so you would take the resultant average vector that would be right here. This is the resultant vector, and so I usually squiggle out the original vectors when I take an average, and so there's no vector to cancel with this one, so you would say that does have a dipole moment. There's some molecules that have polar bonds that do not have dipole moments. So how do we know? Well, it's when the bond polarities or the vectors are arranged so that they all cancel each other out, as you have here with the carbon dioxide. Notice here, this is an identical carbon-oxygen double bond on each side. And so the vector here pointing towards your more electronegative oxygen. Notice this vector is the same magnitude as this vector. So since they're the same magnitude but they're opposite in direction, they cancel out. So this has a net of no dipole moment because the vectors cancel. Notice the symmetry in this molecule. It's a perfectly symmetrical molecule. Typically, as a rule of thumb, your molecules with dipole moments that have more than two atoms, they're going to have a dipole moment if they're asymmetrical. With this molecule, though, the opposed bond polarities cancel out, so you would say that carbon dioxide has no dipole moment, even though it does contain polar bonds. So what I want you to do is, I would like for you to draw the Lewis structure for these 5 molecules. Now pause the video, and because I'm going to go ahead and continue because I have a 10-minute limit here. But then I want you to resume the video. Once you draw the Lewis structures, I want you to try to draw the vectors and then predict if they have a dipole moment. I will start off with the first one here. Carbon has 4 valence electrons and oxygen has 6. That's a total of 10 electrons. So when you draw your Lewis structure, you're going to start with a single bond. That's 2 electrons. We had 10, so 2, 4, 6, 8, 10. Notice we're going to borrow and share here. So this carbon here is going to swing 2 pairs of electrons to the oxygen. So this molecule ends up with a triple bond in your final Lewis structure. Now notice when you're looking at your electronegativity table, carbon is less electronegative than oxygen, so the vector is going to point towards the oxygen, and this is the only vector you can draw. So yes, this does have a dipole moment. I'll put DM for dipole moment. If you draw the chlorine, you got a total of 2 times 7 is 14 electrons, and when you draw this Lewis structure, you get a linear molecule. Now here, if you look, you have the same atom, so you cannot draw a vector here because this is not a polar bond. The delta X here is less than 0.4. In fact, it's 0, so there's no dipole moment because it's a non-polar covalent bond. So you cannot draw a vector. With the SO3, you have 6 electrons here, plus 3 times 6 gives you 6 plus 18, which gives you a total of 24 electrons. So you put your S and you put your 3 oxygens attached to them. That's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And you kind of run out of electrons.